And let's do share screen. Okay, today we're going to look at another thermodynamic function. Remember, we've looked at delta E and delta H and delta S. Those are three of the state functions that we've talked about. Uh, uh, delta E was the internal energy change that takes place in the process. Delta H represents the heat flow that takes place in the process. And delta S is the change in the disorder or randomness that takes place when a process is occurring. Now, the nice thing about delta G is it helps us to identify those processes that will happen by themselves. And they're the ones that are really extremely important. Well, there it is. Okay. Okay, let's do this. And okay. Now, the well, I'm having trouble finding. There's what I want. Okay, the delta G helps us identify those processes that take place by themselves. And the reason why they're so important is that a process that happens by itself can actually do work for us. And we're kind of lazy. We like to have something else work for us. And this allows us to find chemical processes that can do work. The Gibbs function is defined as G is H minus TS. And so it's going to have a flow of heat that acts toward a driving force and a change in entropy that acts as a driving force. And if you look back a lecture or two ago, we looked at those processes and saw that if a process is giving off energy, we expect that to be spontaneous. And if it's increasing disorder, we expect that to be spontaneous. So the Gibbs function puts both those together and allows us to create a function then that the, let's go, is that crazy? That allows us to find the processes that will do useful work. If delta G is negative, the process can do work. So we're looking for those processes that have a negative value for delta G. If the process has a negative value for delta G, it can take place by itself. If it's positive, that process can't take place at all unless you somehow make it happen. It's not going to happen by itself. So every spontaneous change can do useful work. Now, what do we mean by useful work? I would think all kinds of work is useful, but it's not. When you carry out a process in a chemical reaction, the volume will change because the identity of the substances change. For example, if we started out with 6 moles of gas at 1 atmosphere pressure as the reactants, and we went to 3 moles of gas in the products, then the volume would decrease. And that would be part of the heat flow we measure out. The universe, the atmosphere, the surroundings would be doing work on the system. So it would put heat into the system when that took place. It put joules of energy into the system when that process took place. And that has to happen because you go from one set of reactants to another set of products. Now that PV work is not what we call useful work. That process has to take place no matter what. And so we're looking at excess over that, work that can be done in excess of that PV work that has to be done. And that's what we mean by useful work. So the decrease in the Gibbs free energy for a process is equal to the maximum amount of useful work that can be done. Now, you remember in experiments, work is defined as minus FDL, the force applied. So you can do the process that can do useful work, but you can do it in the lab in a way that it does no work at all. For example, when we talked about internal energy, the key to that whole discussion was that the internal energy that takes place is the amount that you have to put into that system to make it take place. And if you have that system in a closed container at constant volume, then no work gets done. But if you do it the same process out in the lab in your Bunsen burner, work gets done. It's that PV work of expanding against the atmosphere or contracting, depending on the direction sign of the volume change. But if you carry out the process at constant volume, it does no work at all. Now, the internal energy change is the same no matter how you do it. The enthalpy is the same no matter how you do it. The Gibbs free energy change would be the same no matter how you do it, but it doesn't mean that you're going to get that much work out. Then you have a choice of the way you want to carry out the process, and you can carry it out in a way where there's no work done, or you can carry out a way where you have lots of work done, but there's a limit. The maximum amount of work you can get in addition to that PV work is the change in delta G. So this is one of the best of all of the functions we've looked at, because it allows us to look at constant temperature and pressure at a process that's the conditions we're apt to find in the lab, and we can determine whether there's work done or not, and how much is the maximum amount of work that can be done. So the amount of work you actually do can be anywhere from 0 up to delta G. It cannot be greater than delta G, though. That's going to be the limit. Now, temperature affects the spontaneity of some processes because of this function here. Delta G would be delta H minus T delta S. So you see, there is a change in the temperature. I mean, if you change the temperature, you're going to change the value of delta G dramatically. But if you change the temperature, you really don't change delta H or delta S very much. So we can still use our delta H for a process at some temperature other than 25 degrees, and we can calculate the delta S at some temperature other than 25 degrees, and we can just multiply T times delta S and subtract that from delta H. We'll get the delta G at the new temperature. So if delta H is less than 0 and delta S is greater than 0, delta G is going to be less than 0. So it's going to be spontaneous no matter what value you put in for temperature. If delta H is greater than 0, this term is positive, and delta S is less than 0, this term is negative, then delta G is less than 0 at high temperature. So you're going to have to get this temperature up high before you get a negative value possible. They subtract from each other. If delta H is less than 0 and delta S is less than 0, delta G is going to be less than 0, so it'll be spontaneous at low temperature. And of course, if you take the other possibility, delta H is greater than 0 and delta S is less than 0, then delta G would be greater than 0, and it's going to be spontaneous at delta G. That's not going to be spontaneous at all. that sign is wrong. It's greater than 0. That sign is correct. So this is greater than 0. You need to make a note on that, and I'll fix it when I get back. That should be not spontaneous at any temperature if delta G is positive. Okay, all right. Now, I need to clear that annotation from the other side.
Will you
Okay.
go back to that slide for just a second for me, Dr. Pearson?
I'm sorry?
Will you go back to that previous slide for me for just one moment so I can finish my note?
Okay. Okay. The Gibbs free energy is defined relative to a standard state, just like we had for delta H. Now, if you had a true value for delta G at 0 at some value. Now, I have a concept mentally that that's got to be true. I mean, if it has a value and you decrease it and you decrease it, it seems to me you ought to be able to get to a 0. So I have a concept that there is a true 0 for delta G, just like I did for delta H. But we can't ever see the absolute values. All we can see is changes. Excuse me. So if I look at the free energy for state 1 from this true 0, and then I'm going, this is going to be the change from here, and this is going to be the free energy going to my state 2 is up here somewhere. Now, that's the free energy all the way from true 0 to state 2. If I subtract off the value from the value up to state 1, I get delta G is just that particular value for state 2, that difference between the two. Like that. So this is the difference I'm going to get when I take state 2 and subtract off state 1. Now, if I look at some reference state that I can define, and we're going to use the same reference state that we used for delta H. The 0 is going to be the elements from the periodic table in whatever form they're in at 25 degrees and 1 atmosphere. That's going to be our 0. So if I'm thinking about oxygen, for example, O2, it's diatomic. So we're not talking about ozone, O3, we're talking about O2. It's gaseous at 25 degrees and 1 atmosphere. So anytime I see an O2 in a system at 25 degrees and 1 atmosphere, that's my reference. That's a 0 value for delta G and delta H as well. Now recall it wasn't for delta S, because delta S will be something different. I'll show you in a minute. Okay, so if I go from this new reference state up to state 1, it's that far. If I go from this new reference state up to state 2, it's that far. And then if I go from state 1 to state 2, then I'm going to take the difference to state 2, and this is the value at state 1. If I subtract them off, you see I get the same difference. So whether we use a true value, which we can't, or use a reference value, it's still going to be the same difference. And that's the way we do. And we are free to choose whatever reference state we want to, but we have decided already for chemists, it's going to be the elements in their normal natural form at 25 degrees and 1 atmosphere. That gives us our reference state. Okay, now I want to make a point that's I've not seen made in books anywhere, but it's critical to understand this because we're going to use this delta G in a way in a moment that's really going to be greatly useful for us. But you need to understand this. Here's a reaction, N2 and hydrogen making ammonia. And there's a correct stoichiometry. 1 mole of N2 and 3 moles of hydrogen make 2 moles of ammonia when we balance it. The reference state is the elements in their reference state at a partial pressure of 1 atmosphere. Not a total pressure, a partial pressure. So when I'm talking about this standard state for this reaction, I'm talking about a big container that's got nitrogen in it at a partial pressure of 1 atmosphere, hydrogen in it at a partial pressure of 1 atmosphere, ammonia in it at a partial pressure of 1 atmosphere. By Dalton's law, the total pressure is 3 atmospheres. Now, I've looked at the textbooks, and most of them say it right, but they lead you to the wrong conclusion. They say the standard state is 1 atmosphere, and then they start applying that to reactions, and they talk of it as if the reaction was taking place at 1 atmosphere. It's not in the standard state. In this case, it's 3 atmospheres. By Dalton's law, it's the total pressure is the sum of the partial pressures. Now, the other critical thing about that is by Raoult's law, we now have the concentration of everything that make up the standard state. The mole fraction times the partial pressure over the total pressure is the mole fraction. And so this standard state, 1/3 of the moles in it is nitrogen gaseous, diatomic. 1/3 of the moles is hydrogen, and 1/3 of the moles is ammonia. Now, it is not in the stoichiometry. It's not 1 atmosphere of nitrogen and 3 atmospheres of hydrogen and 2 atmospheres of ammonia. No, no, no. It's not that. It's each substance has to be at 1 atmosphere pressure to define the standard state. And that means the standard state is giving you a set of concentrations. And we're going to be interested in which direction from that set of concentrations will this reaction go spontaneously. Now, technically, what we would have to have is a container so big that I could go in and take out 1 mole of nitrogen and not change its partial pressure. I could go in and take out 3 moles of hydrogen and not change its partial pressure, and make 2 moles of ammonia and not change its partial pressure. So you see, this is really a state that couldn't absolutely exist, but who cares? It's a defined state, and we can define our reference state any way we want to, but by defining it the way we have fixed the set of concentrations that you have in this mixture, and we're going to decide if delta G decreases, negative, going from 1/3 of a mole, 1/3 of a mole, and 1/3 to less than a third, less than a third, more than a third. If that process gives a delta G that's negative, it will go to the right, starting at that standard state. But if that's not the case, then it won't react. It'll go the other way. So that is a really, really critical point. I think I've never seen a book that does a good job with that. Ours doesn't either. I already did that, so let's go back to here, go back over here. All right, now, so delta G is, now I'm making a point here too that's really subtle. You see these delta G's up here, they got little superscripts on them. That means the standard state value. This delta G doesn't have a superscript on it. So that means at whatever concentrations you are, whatever you put together in the mixture, if the change from that set of concentrations toward more product is 0, you're at equilibrium. If that change is less than 0, negative, you're going to go further to the right to achieve equilibrium. And that'll come up in a little concentration I'll show you here. But if I take that first equation, delta G is delta H minus T delta S, that's called the Gibbs-Helmholtz equation. So if I set delta G equal to 0, delta H is equal to T delta S. So this is the relationship between delta H and delta S when you're sitting at equilibrium. So the free energy of any mixture is determined by the composition of the mixture. The free energy with a little superscript is the one that has 1 atmosphere pressure of each of the substances that are gaseous present. Now, the free energy of a mixture of ice and water can be lowered if the mixture is changed to water, if you're at 25 degrees. So at any temperature greater than 0, that's going to be the case. The equilibrium temperature for freezing water is 100 degrees Celsius. And if you put in the delta H for that process and the delta S for that process and solve for the temperature, you ought to come up with 100 at 0 degrees. That would be the temperature where equilibrium would happen, and delta G would be 0. So at any temperature greater than 0 degrees, ice will melt. Hey, you know that. You get an ice cube out of the fridge and set it in your glass, it's going to melt out here. But below 0 degrees, the free energy of the mixture is lowered if the water is changed into ice. So at 0 degrees, you can have any mixture of water or ice, and that's stable and thermodynamically at equilibrium. But if you lower the temperature of that ice-water mixture, eventually it's going to all freeze. If you raise the temperature above 0 degrees, eventually it's going to all melt. So the free energy is temperature dependent, and it changes with temperature. There's a temperature where you will achieve equilibrium, and then at any other temperature, you have a spontaneous direction. So when we are, if I look over here, here's a little cartoon that I drew showing a reaction. I deliberately did not use coefficients of 1 up here. I just used 2, 3, and 4. It doesn't matter how it's how it's set up. Let's say that Kp is equal to 4. Now, if these are all gases, then that would be the partial pressure of C to the 4th power divided by the partial pressure of B to the 3rd power and the partial pressure of A to the 2nd power at that equilibrium temperature is 0.5. The way I've got this set up and the way I drew the data. So here's the free energy as you've changed from all of it is in the form of A plus B over here. And over here on this side, 100% reaction, it's all C. So this is the way the free energy would change as you change from all A and B to all C. This is a curve you would get if you did that. Now, I've highlighted a point I'll point out in a minute. So at equilibrium, there's 3 things in here. So 1/3 of that at 0.333, 33.33% reacted, this is going to be our equilibrium value. Delta G is greater than 0 if I go on this side. If I go this direction, final minus initial is going to be a negative value going to this direction, a positive value going to the right. So if I'm at equilibrium, that's this point right here that I highlighted. That's the minimum free energy that mixture can have. And that is where equilibrium will be. And so delta G is going to be 0 at equilibrium. Notice I am using the delta G without the superscript. That's intentional. We're not talking about the standard state value. That's this point right here that I'm highlighting now. That was the standard state value. Delta G superscript was at that place. This now is the equilibrium is going to really occur where the free energy is at its minimum. And then, of course, if I'm on this side, going this direction is negative. Final minus initial will be a negative number. So on this side of equilibrium, the spontaneous direction is toward equilibrium. On this side of equilibrium, the spontaneous direction is toward equilibrium. That's the point is the spontaneous direction is always toward equilibrium from wherever you are. So the sign of delta G without the superscript can be used to predict whether a reaction is spontaneous going from whatever set of concentrations you have at the moment. Sign of delta G can be used to predict whether a reaction is spontaneous starting from the standard concentrations too. Now, when we looked at this one, remember if we're at the standard concentration values, the delta G would be 0. Delta G superscript would be 0 at that point. Now, if the process is not spontaneous in one direction, it is spontaneous in the other direction. Remember, when you change the direction of a reaction, you change the sign of all of its functions. All the state functions would change signs. Here's some problems with this. So we're looking at a reaction 2NO gas plus O2 gas goes to 2NO2 gases. And we're expected to define the standard state, calculate the delta H and delta S and delta G for that mixture. And now these are with the superscripts. Okay, the standard state. It's a mixture. It's containing what? 1 atmosphere partial pressure of the NO, 1 atmosphere partial pressure of the O2, and 1 atmosphere partial pressure of the NO2. So that defines the standard state. In this case, there's 3 things involved in the reaction that are gases. So the total pressure of our standard state mixture is 3 atmospheres. So we've defined the standard state. And all mole fractions, the partial pressure of the NO is 1 atmosphere. The partial pressure, total pressure is 3 atmospheres. Mole fraction is 1/3. Mole fraction is going to be 1/3 for all of the substances present. Now we can use our table data in the back of your book to calculate the delta H. We're going to take twice the delta H formation of the product, NO2, and we're going to subtract off twice 2 times the delta H formation of NO. We don't need oxygen because oxygen is diatomic and gaseous, so it has a 0 value for its heat of formation. It's the standard state. If we do the math that's implied there, we get minus 113.06 kilojoules. That's the delta H for this reaction. We don't need to go in the lab and measure it. We can just go to the back of the book and calculate it. And my Gen Chem 1 students this week, are doing delta H of reactions where they had to measure it. So, okay, now the entropy is going to be the third law entropy of twice the third law entropy of NO2 minus twice the third law entropy of NO and minus the entropy of O2. Now, O2 does have a reference value because we're going all the way from the perfectly ordered state is 0. So there is an absolute entropy for O2, and we have that listed in the table in the back of your book. So here are the numbers. If we plug in the numbers and do the calculation, we get the delta S is minus 145.34 joules. Now notice the difference in the units. These are in joules per mole per Kelvin, and this delta H is in kilojoules per mole per thousand per Kelvin. And so this is the unit of the, and you expect these values. Now about the sign, well, let's go up here. The delta H for this process, it's an oxidation process. Almost always they're negative. They give off energy, and that's the sign we got. The delta S we can get much easier because I've got 2 moles of gaseous products and 3 moles of gaseous reactants. So that means the entropy decreased in going from this state to this state. There's 3 moles of gas on the left and 2 moles of gas on the right. The product is a more ordered state than the reactants is. So products minus reactants is going to give me a negative number. And so that's what it should be. Now I can calculate delta H or delta G from these values, and or I can calculate from the sum of each of the formation of products minus reactants. We could do it either way. And I think I've done it both ways. If I do the delta H minus T delta S from what we did up there, now be very, 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 very careful. This is in joules. I had to change that to kilojoules in order to connect it with the delta H value. So it was 145.34 joules, so that would be 0.1453 kilojoules per mole. So when I do that math, I get minus 69.75 is what I get from delta H minus T delta S. Now let's look at what we would get if we took the delta G values from the tables at the back of the book. And these are the numbers. I've got 51.84 for the delta G of formation of the product. And I've got 80 plus 86.71 kilojoules per mole for the heat of formation, or the free energy of formation of NO. Notice I don't subtract off an O2 value because it's diatomic and gaseous. So its standard delta G of formation is 0. If I combine these two, I got this number. So you can see that these agree to plus or minus 0.01. Now, don't expect that always to happen. This was a very good example and a very simple reaction where it did work out pretty well. But these numbers won't necessarily be exactly the same number, but they ought to be pretty close to the same number. Now, will the mixture of 1 atmosphere of NO, 1 atmosphere of O2, and 1 atmosphere of NO2 proceed to the right or to the left in achieving equilibrium? Which direction is spontaneous? Well, this is the standard mixture. So if I look at the delta G superscript, going to the right, it had a negative sign when we calculated it across on the other slide, negative 69.74. So it is spontaneous to the right from the standard state as well. How will the temperature affect this reaction? Well, let's look at it. There's delta G is delta H minus T delta S. So looking at my numbers, the delta H value is minus 113.06. I'm subtracting off T times a minus 145.3. Now that minus times that minus is going to be positive. So that means this term is going to get more positive as the temperature increases, which means it will be negative. It was negative 69.73 at this number being 298. If I increase the temperature, this term is actually positive, so it's going to continue to subtract from this negative value. So it's going to become less and less negative as the temperature goes up. So it will achieve some equilibrium at some temperature. So increasing the temperature will make this reaction less favorable. So calculate delta G at 100 degrees C. Okay, we can use delta H and T delta S to do that. All we got to do is plug in the temperature to the equation. And the temperature, remember, has to be in Kelvin. So 100 degrees is 373 Kelvin. And so we get minus 58.85. And notice it is less negative than it was at 25 degrees. Okay. So it's less favorable at the higher temperature, which is what we expected. Now here's your checkpoint on that. It's a very similar reaction, but it's got an extra thing in it, some 3Cl2s. So you can do this exactly the way we did it before. Here's a table of the data that you have, and you're to calculate delta H and delta S and delta G from the table. Calculate delta G from delta H minus T delta S. And what's the mole fraction of Cl2 in the standard mixture? Now don't just jump on the bandwagon and say everything I've seen has been 0.333. This one's not going to be 0.333. Will the mole fraction of Cl2 increase, decrease, or not change in reaching equilibrium from this value? So I'll give you a hint. You need to look at the sign over here of delta G and delta H. And remember, if you want the mole fraction of this to increase, you're wanting it to go to the right. So you're wanting delta G to be negative. Okay? Will the reaction be more or less favorable at 50 degrees than it is at 25 degrees? Remember, the data here, you're getting everything calculated at 25 degrees. So you're going to increase the temperature, and all of this is going to be very much like the problem that I just did for you. But you do need to do these exercises for yourself and be sure that you are able to do them. Again, if you need help, you can email me. I really do prefer that you work with each other on the discussion groups, because it'll be much better if you figure out how to do it than letting me do it for you. I already know how to do it. Okay, all right. Well, that's all I'm going to do in this lesson. I'm going to stop the recording now, and then let's see. I think I'm going to stop the recording. Stop recording.